Welcome to part 2 of the kangaroo2 tutorial for simulation and prototyping. We're going to start this second stage of working with meshes. And so what we did previously two-dimensionally with just a two-dimensional hanging chain shape, now we're going to do three-dimensionally with a mesh. And the first example that I wanted to use in terms of thinking about our courtyard space is just a really simple real world example, really great example of Caesar's Portuguese pavilion at the World Fair. And so it's a concrete canopy that drapes between these two buildings. We can see a couple of views of it here. And so while there's a lot going on here, there's a lot that we're not going to talk about right now related to this building, I just thought it was a nice example so that we could see a surface that kind of drapes, and we could play with that a bit. And so let's look at how we would start modeling this. The first thing that we're going to need to do is to create a surface. And let's create where we used a curve previously, let's use a surface container. And I'm going to model in Rhino a very simple planar surface from corner to corner. And we go from one corner of the courtyard all the way out to the front edge of the courtyard. Let's move this up. And I'm going to rotate it. Just a little bit. Maybe move it up a little bit more. And we can always come back and we can modify this. And maybe the last thing that I'll do is just scale 1D in plan. So if I select it at its midpoint, I can pull it in on the sides. So now we just have a rotated flat plane up on the top on the surface. So let's set the surface container to that one element. I'll then hide that surface, and now we have the grasshopper representation of that. So the first thing that we're going to have to do is to turn this into a mesh. And the reason why we use a mesh is that the kangaroo2 solver uses the grid embedded within the mesh as a way to look at the springs and the strength of those lines. And so we have two options to create a mesh. One is a mesh brep, and the other is a mesh from surface. And I'm going to default to using the mesh from the surface because it allows us to set the U and the V count of the mesh, which U and V relates to a NURB surface, but at least when we do this, it gives us that level of control. And so the surface will be the surface. And then let's make, I don't know, a 40 element slider. We can copy it. We can set this for the two U and V. I'm going to turn it down now. However, let's turn it down to somewhere around 20. And again, what's nice is being able to have these set to be two different dimensions, because one, we probably want the mesh to be the individual elements or patches to be one-to-one kind of square relationship. And so we can add more U or V counts depending if our surface varies from one dimension, one side to the other. So the first thing that we can do is plug our mesh into the show, and we can hide our mesh. So now we can see a sense of those points. Let's turn our solver off for a second. And let's the solvers being on is nice so that we can see the vertices. So now that we have that, let's also, and this was the trick I was using before that did a couple of things, but let's deconstruct our mesh so that we can actually pull those vertices and use them for other things. But we can hide this given that we have the solver visualization with those. So we're showing the mesh, and that's good. We need to set some loads. In this case, we're not going to use, I mean, we could pull all of these vertices and add them to these points. There's also within kangaroo2, there is a Vertex Loads that this will simply just pull all the vertices from the mesh and use those. So let's swap out our load for Vertex Loads. And what we'll plug into Vertex Loads is simply the mesh. Plug in our mesh, and let's set the Vertex Loads to be -1. Plug that into the strength, and then plug the Vertex Loads back into the merge. Spot 3 is open, so we'll use that. The line length, we used this previously. Let's delete the line length, and let's add in a new one, which is also from Goals Mesh in kangaroo2, that is edge lengths. And so as we set edge lengths, we're also going to connect the mesh. Our length factor, let's set this to be 1. So I'm going to use //1. And then the strength, let's start this with 1,000. So //1,000 and then enter, and that'll be our strength. So the last thing that we have to do is set our anchor points. And in this case, like the CISA model, what we want to do is to set 2 of the edges to be fixed. And so then that allows the surface to drape between those. And so let's get the anchor points. The way that I'm going to do that is I'm going to partition the list. And so we have a list, and let's set a couple of panels down here. So let me plug in the vertices. And this is just simply a list of points that is right now 440 long, 441, I suppose. And let's plug in this list of vertices into the partition list. And let's set the size of this to be equal to the V count, but +1. And the reason being is that the size doesn't count the 0, or one of these doesn't count the 0. So let's create a really simple expression. I know that we can do this within the size over here, but I think it's just better to make this clear, especially if you're going to go back and look at this later. So we'll zoom in a little bit. We only need one input, and we'll change the format to be x + 1. What's nice about this is that if we change the slider, we're not having to change the size of the partition. So plug that in for size. And let's copy our panel. You can see what happens with a partition. So what this does is it now breaks the list down into 21 different elements. And that's the difference, because when we set the slider to 20, the slider is not counting the 0, the list is. And so we end up with 21 here. Let's take a look at that and see how that looks. So how to pull these chunks out. We don't want all of them. If I turn that on, we can see that's all of the points. All we've done is just categorize the data. We haven't actually separated it out. And to do that, we're going to use the list item. Now we'll do list item. That defaults to 0. And so we can hide the partition list. And now the list item, we can see that this is all of these points along one edge. That's really good for us. Let's copy this list item. And then the easiest way to do this is just simply to reverse the list, which now will also put, it just flip-flops the data within the list. And so that our last items became our first items. Because the index defaults to 0, it's the first grouping of numbers in this list, and it's the first grouping in this list. But now we have our 2 edges. I'm going to get rid of the 2. Well, while we're here, why don't I just add one more panel, and you can see that last transformation just gave us the first 21 items in that list. And we could flatten this if we wanted, right? Which is just now 21 items in that list. So why don't I delete these panels? So what we have now is some loads on all of the vertex points. We now have 2 rows of anchor points. And let's turn on our solver and let's see what happens. It is very, very deep because I forgot to connect the edge lengths into the solver. So what we can see it's happening is just drooping all the way down. Let's plug in our edge lengths. It's bouncing a little bit, but we can also just hit the reset. I'll even zoom in. So now we can see our mesh relaxing and draping into the space. So let's see, let's hide our initial surface. We don't need that anymore. We can hide our bouncy solver. We can turn on our geometry. Actually, there's our clean tree. And we can even hide our list items and our point there. So this is a really simple, just draped surface to create a really simple canopy in that space. Let's add one more thing, or let's change a couple things. Not that we need to do this, but what if we changed the dimension? You see this, or change the number of divisions in our mesh surface. It gets a little confused, and anytime that I change the mesh, what I like to do is just reset the surface or reset the solver. Then it kind of starts more simply. Oh, my computer's a little slow right now. And let's look at it. We can change some of our parameters. We can change some of our parameters, and we can get this to drape deeper if we wanted. We can do that through one of two things. We could either add more load or reduce the strength. So let's go from 1,000 to 500. Now we can see the surface drops a little bit more. We might just want to see the underside as we look through the canopy. What I'd like to do is just add one more element. Let's add a few more anchor points. And an easy way to do this would be to, from our partition list, which broke them into basically rows and columns, or let's say it broke, what this did is it broke it into rows. So let's say the rows are moving horizontally in terms of the orientation on the screen. What we can do is we can flip the matrix, which sounds like an epic command. And flipping the matrix basically flip-flops your data from rows to columns or vice versa. So watch what happens when we plug this in. Let's grab a list item. We don't need to reverse it. We'll plug this in. And let's add, so right now our division is set to 34. So maybe we'll set this to be 40 as a slider, as our index, and let's hold down Shift and add this to our anchor points. So what we see along one of the edges is a new set of anchor points. And so if we reset, just to be sure that this is working correctly, this line, if I turn on that list, we can see these are a set of anchor points. The anchor points are the starting position of the mesh, and it holds them in that location. And so what we see is this draping out from either side from there. And as we turn down our slider from 40, we can move. The wrap was on, which is why it was on the other side. So if I turn wrap to false, if I exceed the number, it will just give me an error instead. So here's the end of the surface. Now it just turned orange because we exceeded the number of our list. But I can move this to the center or a third point within the surface. I could add another one, which is what the example was that I showed you, and we can set this to be 17, 18, and we can just hold down Shift and add this to the index. And choose a location for that. So now we've got kind of line of structure, let's say through the middle there. And let's just rotate this and take a look at that. And what's happening, what makes sense, is that because we're applying loads to all of the vertices, these edge conditions are not held. And so what we have here toward the right are 3 edges. And so that's draping down. Through the middle, it's held along 4 edges, so it drapes less. And then on the other side, it's held on 3 edges. So we could now, with these 2 sliders, move these in and out. We could also set these to be explicit with an expression to be at the 1/3 point and the 1/3 point, or 1/3 and 2/3. And so if we were to change the count, they would always be at the 1/3 and 2/3. But here's our first example, and hopefully it gives you a nice sense of continuing to use the same elements, anchor points, loads, and then the definition of the springs or the lengths, and managing this data in slightly different ways. So we'll stop here for the second tutorial, and then I'm just going to break out the 2 remaining types of examples, which will be similar but different type of form, slight variations with these solver input elements. Let me know if you have any questions, like the video, subscribe to the channel, and we'll pick up the next tutorial whenever you're ready.